Hello, and welcome to a summary of curve sketching. My name is Tuesday J. Johnson. I'm a lecturer at the University of Texas El Paso and an assistant professor at Doña Ana Community College. This lecture is for Math 1411 at UTEP. It's calculus. We use Larson's 11th edition calculus text. This is Chapter 3, Applications of Differentiation. Section 3.6, a summary of curve sketching. Now, all of this comes together using first derivative, increasing and decreasing, maximums and minimums, the second derivative with concavity. Also, the second derivative test tells us some maximums and minimums. We'll use limits at infinity to look for horizontal asymptotes, and we won't forget our basic pre-calculus knowledge of vertical asymptotes and the like. So it's all coming together. If you need to review any of those before you come here, they're all on my YouTube channel, or if you go to UTEP, they're also on Blackboard. So check those out if you need to. There is a video that accompanies this section on my YouTube channel also entitled Curve Sketching. It's one example in excruciating detail that allows us to draw a graph without a graphing calculator. In this lecture, I won't get into such detail on each example because it would be forever long. It really would. So I'm going to do the generalities, of curve sketching here. But if you want one example complete, check out that second video entitled Curve Sketching instead of the summary of curve sketching. So here's some guidelines for analyzing the graph of a function. First, we determine the domain and range of the function. It's nice to know where we're working. We're going to determine intercepts, asymptotes, and symmetry of the graph. And steps 1 and 2, those are all going to be from the original function. Then we're going to locate the x values for which the first and second derivatives are either 0 or do not exist. We're going to use those results to determine relative extrema and points of inflection, increasing, decreasing, concavity, and the like. So here we go. If y equals a negative 2x to the fourth plus 3x squared, we know from pre-calculus that the graph has both ends facing the same direction, and that's because it's a fourth degree polynomial. Anytime we have an even degree polynomial, either the end behavior is both ends go up or both ends go up. Think of parabola, and it's true for any even powered degree polynomial. Because it's negative, that tells us it's going to be generally going down. It might have some stuff going on in the middle, but the two ends are going to be going down. We could use infinite limits here in calculus to conclude the same thing, but why use a mallet when a little hammer will do? We can find the x-intercepts by setting this original function equal to 0. Let's factor out an x squared. Factor out an x squared, I'm left with negative 2x squared plus 3. Each factor gives me a 0, x equals 0, and x equals plus or minus a square root of 3 halves. We know the y-intercept is at 0, 0. So our y-intercept and x-intercepts correspond, and no asymptotes because we have a polynomial. So those are all the things that we can find just using the original function. Now we can use the first derivative. In the first derivative, y equals a negative 8x cubed plus 6x. We can factor out a negative 2x. I'm left with 4x squared minus 3. So I'll end up with an x equals 0 of a critical number, and x equals negative square root of 3 over 2, and x equals positive square root of 3 over 2. Now square root of 3 is a little less than 2, so I know this fraction is bigger than a half, but less than 1. So I can pick some some test values. We'll put those test values on the next screen. Once we have our critical numbers, now we can use test points. I'm going to use negative 2. Negative 1/2, a positive 1/2, and maybe 10. I don't know, I'm feeling 10 today. And when I input this into the first derivative, I know that when x is negative 2, this first part is going to be positive. Negative 2 squared is positive, 2 squared is 4, 4 times 4 is 16, 16 minus 3 is positive, so I know when x is negative 2, the first derivative is positive, so we're increasing. When x is a negative 1/2, in my first piece of the factored derivative, a negative 2 times a negative 1/2 is positive. Negative 1/2 squared is 1/4. 4 times 1/4 is 1, and 1 minus 3 is negative. I don't care what the number is, I care about the signs. So at negative 1/2, I will be decreasing. My first derivative is negative. Now, the positive 1/2 in the square, it doesn't change what's in parentheses. 4x squared minus 3 when x is 1/2, still going to be negative. But now out in front, the negative 2x times 1/2 is also going to be negative, and a negative times a negative is positive. Putting in 10, we'll have a negative in the front, positive here, negative times a positive will be negative, and we have increasing, decreasing, increasing, and decreasing. Looking at the second derivative, now my second derivative, I'm going to put this in blue. Second derivative is negative 24x squared plus 6. If I factor out a negative 6, or divide both sides by negative 6 when I set the second derivative equal to 0, I'll get 4x squared minus 1 equals 0. So x squared equals 1/4. So x equals plus or minus 1/2. So I have a negative 1/2 and a positive 1/2. Let's pretend that's a 2 there. 4 possible points of inflection. Let's bring this all together. With our second derivative, once we have the possible points of inflection, we're going to use some test values. Maybe we'll use 0, 1, and negative 1. In the second derivative, when I put in negative 1, let's put negative 1 here instead of the factored form. Negative 1 squared is 1. And negative 24 plus 6, that's going to be negative. Negative is going to tell me that it is concave down. When I put 0 in, 0 squared is 0 times negative 24, still 0. When I add 6, that's positive. I don't care that it's 6, I care that it's positive. And then when I put in a positive 1, I realize, hey, this is an even function. So whether it's a negative 1 or a positive 1, when I insert the value, it's still going to be the same. I'm going to have a negative. So it's concave down, and then up, and then down again. All those things we learned in 3.3 and 3.4 for increasing and decreasing functions and concavity. So we found some locations of important points using the derivatives. Now we want to find the corresponding y values in the original functions. Now I know there are maximums, negative square root of 3 over 2 and positive square root of 3 over 2 as x values. To get the 9/8, the y values, I always go back to the original function. I know there's a minimum at 0. I happen to know 0, 0 is a point on the graph, but if I forget that, the minimum at 0, I can evaluate and I can see that, yeah, 0, 0 is going to be a minimum. Possible points of inflection, and they are actual points of inflection. We found that the concavity changes. When x is a negative 1/2, I evaluate my function, and I get 5/8. This is an even function. All the exponents on the polynomial are even. And so when x is positive 1/2, we get 5/8 as well. So the derivatives tell us where to find these values. The original function tells us what the heights, what the y values actually are. Remember, this is a sketch, it's not perfection. We have our intercepts. We also have our minimum. We have a maximum. Both of them. We have inflection points. I will admit, that is not pretty. But it looks pretty close to what the original function does when we look at Desmos. So, pretty good. We'll take it. It gives us a good basic idea of what we've done. Let's look at a rational function with a quadratic numerator. F of x equals 2x squared minus 5x plus 5 over x minus 2. First of all, the numerator is never 0. The discriminant is negative if you try the quadratic formula. So we know that there are no x-intercepts. We know there's a vertical asymptote at x equals 2. X equals 2 is not in the domain of the function. The y-intercept, if I put in an x value of 0, everything with a variable cancels out, and I'm left with 5 over negative 2. So a negative 5/2 is my y-intercept. If I compare the degrees of the numerator and denominator, I see the numerator has a larger degree, so the limit as x approaches infinity does not exist. And I also notice, using pre-calculus techniques, since the numerator has a degree exactly 1 higher than the degree of the denominator, I could use either synthetic or polynomial division and find a slant asymptote of y equals 2x minus 1. So laying out the asymptotes, vertical, horizontal, and slant, as well as intercepts, is a great way to start your problem. But now we move on to the derivatives. So I'm going to use the quotient rule to find the derivative. You should pause and check my work, make sure I got it right. I'm going to assume I did, maybe stall a little bit so you can find time to hit the pause button. 2x squared minus 8x plus 5 all over x minus 2 squared. Let's look at that first derivative and see what we can glean from it. I know that the first derivative will give us critical numbers, and critical numbers occur when the derivative is 0, in which case the numerator is 0. Pretty ugly, 4 plus or minus the square root of 6 over 2. And when the derivative does not exist, which is when x equals 2. So putting these critical numbers on our number line, square root of 6. And square root of 6 is between square root of 9 and square root of 4. So it's between 2 and 3. For estimation's sake, I do 4 plus 2.5, so that's 6.5. 6.5 divided by 2 is 3.25. So I know it's bigger than 3, but definitely less than 10. 4 minus the square root of 6, 4 minus 2.5. And remember, this is an approximation. I'm not saying that the square root of 6 is equal to 2.5. I'm just saying to get a good idea of where it is on the number line. 4 minus 2.5 is 1.5. 1.5 divided by 2 is 3/4. So I know 4 minus the square root of 6 over 2 is between 0 and 1. I know 2 is between 1 and 3. And since this is a little bit bigger than 3, I know that 4 plus the square root of 6 all over 2 is between 3 and 10. And now I have test intervals. And I know my denominator is always positive. And so my numerator is going to decide the sign. If I put in 0, I will have a positive 5. If I put in 1, 7 minus 8 is a negative 1. If I put in 3, 3 squared is 9. 9 times 2 is 18. 18 plus 5 is 23. However, negative 8 times 3 is negative 24. So that's a negative 1 when I combine them. And when I put in 10, it's going to be overwhelmingly positive. So I have my increasing and decreasing. I have my x values of critical numbers, everything from the first derivative ready to go. Now the second derivative, to find the second derivative, I use the quotient rule from the first derivative and a little bit of chain rule thrown in. Again, if you need to, pause, see what kind of crazy algebra I have going on. I can tell you here that I have factored out an x minus 2 in the numerator, and it cancels with 1 from the denominator, so I'm left with an x minus 2 times 4x minus 8. The minus and the 2 and the trinomial is this x minus 2, one of these, and one of those have all canceled. FOIL, combine like terms, I end up with the second derivative of 6 over x minus 2 cubed. So I have 6 over x minus 2 cubed. Let's put this in blue. I know that the numerator is never 0. The denominator is 0 when x equals 2. I want test values to the left of 2. I want test values to the right of 2. And when I go to the left of 2, say 0. 0 minus 2 is a negative 2. Negative 2 cubed is negative. A positive 6 divided by a negative number, that's going to be negative. Put in 3 for x. 3 minus 2 is 1. 1 cubed is 1. 6 over 1 is positive. I don't care that it's 6. I care that it's positive. And I have my concavity from my second derivative. We found the x values of key points. Now we find the y values from the original function. So I know my maximum, 4 minus the square root of 6 over 2. Look, that's pretty close, 0.8. The y value that goes with it, yes, you have to evaluate 4 minus the square root of 6 over 2 as your x value. Put it in, evaluate. Technology is awesome. You can use a calculator. And these are, of course, approximates as I've rounded to 1 decimal place. The exact value, a value I would put in, say if I was using WebAssign homework, this is the exact value. I use the decimal approximation so I could actually put it on a graph so I know what is this number. 4 plus the square root of 6 over 2 is not something that I deal with very often. We have our slant asymptote. We have our vertical asymptote. I have a maximum. I have a minimum. I have a y-intercept. I am increasing and then decreasing. I am decreasing again and then increasing. All right, the two decreasings in the middle. And if we graph this on Desmos, look at that, not bad. You can see how there's an asymptote in here. And you can see the asymptote maximums, a concave down, concave up. Everything works exactly like we thought it should. We don't have to have a nice graphing calculator in order to find the graph. We could do it on our own. Alright, so this is probably going to be the last example. I don't know, we'll see. That's right, I don't know what's coming any more than you do. Examples, analyze and sketch. Y equals x times the square root of 9 minus x squared. Now we know that x, we could put anything in for this x. However, under a radical, we know that the radicand, the thing under the radical, must be non-negative, so it has to be greater than or equal to 0, in which case our domain is going to be from -3 to 3. -3, 0, and 3 will also give us our x-intercepts, as that's where the function is 0. The y-intercept is also given as one of the x-intercepts, so x-intercept, y-intercept at the origin. No asymptotes. That's it. That's all we can find from the original function. So let's find the first derivative. Product rule, x times the square root. So anytime we say times or multiply, if you want to be sophisticated about it, we know we have the product rule. So we'll have x times the chain rule, finding the derivative of the square root of 9 minus x squared. Don't forget about the derivative of the inside. Plus second times the derivative of the first. That's the easy part. The 2's cancel. The -1/2 ends up in the denominator. I'll have x times x for the x squared with the negative in front of it, plus the radical. In order to add these two, I must multiply the numerator and denominator here by the square root of 9 minus x squared. Let's put a 2 up there. In order to get this term. And when I multiply the numerator by that radical, I just get the radicand, right? I squared a square root. There we go. Now that I have a common denominator, I can combine like terms. This is 9 minus 2x squared. A nice tight denominator like this, instead of multiple terms, makes it so much easier to find your second derivative. Now, my first derivative is 9 minus 2x squared over the square root of 9 minus x squared. I know the derivative is 0 when the numerator is 0. So that's 3 square root of 2 over 2, plus or minus. The derivative does not exist at the endpoints of the domain. So at plus or minus 3, we're done. We know there's nothing to check on either side of those. So where would we put these on a number line? Square root of 2 is approximately 1.4. 1.4 times 3 is 4.2. 4.2 divided by 2 is about 2.1. So I'm going to put my endpoints, -3, 3, -2.1, which I'm going to cleverly call -3 square root of 2 over 2, and positive 2.1, which I'm cleverly going to call 3 square root of 2 over 2. My test points, probably a -2.9, a 0, a positive 2.9, just to make sure I've given myself enough room here. When x is 0, the denominator is always going to be positive. So when x is 0, the numerator is positive as well. When x is 2.9, 2.9 squared is a little less than 9. A little less than 9 times 2 is a little less than 18. 9 minus 18, that's going to be negative. So I know I'll be decreasing on the outsides, increasing in between. Now, using the first derivative, again, the quotient rule, a whole bunch of simplification. I'm squaring the square root to square the denominator. I simplify it. This is still looking pretty ugly. So let's do some more simplifying. I want to point out that our first step was the only calculus. This is all algebra. Pause as much as you need to in order to make sure you understand the algebra. Calculus, easy. Calculus is awesome. Algebra, The devil's in the details, and the devil is in the algebra. So algebra is all the details that we have in calculus, and that's what makes it more complicated for people than they need it to be. So after I simplify the second derivative, you have paused at this point to make sure my algebra is correct. I get 2x cubed minus 27x over 9 minus x squared to the 3 halves. I have my original function, my first derivative and second derivative. I know the second derivative is 0 at 0 and at 3 squared is 6 over 2 plus or minus, setting my numerator equal to 0. These last two, 3 squared is 6 over 2 and negative 3 squared is 6 over 2, they're outside of the domain. So the only one that we focus on is the x equals 0 from the second derivative. So if my second derivative has a critical number of 0, I'll use a test point to the left. I'll use a test point to the right. Remember, I can't go crazy and use something like 10. 10's not in our domain. So I'm just going to go simple, negative 1 and 1. When I put negative 1 into the second derivative, negative 1 cubed is negative 1 times 2 is negative 2. But negative 2 plus 27, that's going to be positive. My denominator is in this domain is always going to be positive, so that's increasing. A positive 1 will give me 2 minus 27, which is negative, and that is not decreasing. Let's make sure we remember where we are. Positive second derivative, that's concave up, and a negative second derivative is concave down. Don't forget where you are. So we found some important locations using the derivatives. The y values that go with them always come from the original. So 3 squared of 2 over 2 is a maximum based on our increasing decreasing chart. The y value when I substitute is going to be 9 halves. The minimum, negative 3 squared of 2 over 2 is going to give me an output of negative 9 halves. And a point of inflection occurs at 0, 0. It looks like decreasing, and then increasing, and then decreasing, concave up, and then concave down, end of our domain, x and y intercept. We also have a point of inflection here. Looks good. And I would say that Desmos agrees with me. My points are a little too sharp, maybe a little too steep coming in here. But overall, the general idea of the function can be easily found without a graphing calculator. Thanks again to Desmos.com. I don't remember who told me about them, but that student, I hope they got an A because I love Desmos. And I use it whenever I need a nice pretty graph in my lectures. Thanks for listening.